Okay, so C11 is all about looking at the Earth's evolving atmosphere. So first we start with the history of that atmosphere. And the Earth formed 4.6 billion years ago as a molten ball of rock and minerals. For the first billion years, it was a very hot and turbulent place. The Earth's surface was covered in volcanoes, spewing out gases to form the atmosphere. And the way that we can remember what the original atmosphere contained is the little mnemonic MONC. So we have methane, ammonia, water vapour, nitrogen, but mostly carbon dioxide. Now, our water vapour, nitrogen and carbon dioxide come from the volcanoes. Those are the gases that the volcanoes are spewing out, essentially. Now, we have numerous theories about how the Earth's early atmosphere formed, but very little evidence. So most scientists have based their theories on gas bubbles trapped in ancient rocks, gas bubbles trapped in ancient ice cores, and data from atmospheres from other planets and moons like Venus and Mars. And then there's this mini topic, which is how our oceans formed, or how did water content increase on the Earth? And there's three ways. Number one, the Earth cooled and our water vapour condensed to form liquid water. Number two, it then rained for millions of years, and this caused two things to happen: rocks to solidify and oceans to form. And finally, icy comets rained into the Earth and melted. So about 1 billion years later, the Earth stabilised and the atmosphere was mainly CO2, some water vapour and nitrogen, just traces of methane and ammonia, and with little or no oxygen. And this is similar to the atmospheres of Mars and Venus today, with lots of carbon dioxide and very little oxygen, and it remained like this for a very long time. Then life on Earth began around 3.4 billion years ago with the first simple single-celled organisms very similar to bacteria, and they used the breakdown of chemicals to provide their energy. 2.7 billion years ago, the first bacteria and other organisms like algae evolved. They used energy from the sun and carbon dioxide in the atmosphere to produce their own food via photosynthesis with a waste product of oxygen. Over the next billion years, levels of oxygen increased steadily, and algae and bacteria thrived in our oceans. More plants evolved, becoming more and more complex. More oxygen was released and more carbon dioxide was used up. So the first animals started to evolve. So remember our photosynthesis word equation: carbon dioxide plus water makes glucose and oxygen, with sunlight and chlorophyll on our arrow. Our chemical equation would be 6CO2 plus 6H2O makes C6H12O6. That is glucose, plus 6O2. 6 is in front of everything except our glucose molecule there. Our current atmosphere contains 79% nitrogen, 20% oxygen, 0.04% carbon dioxide, water vapour, all the noble gases like helium, with argon contributing the most. However, with such a high concentration of oxygen within our atmosphere, the earliest microorganisms were disturbed. They weren't used to high oxygen concentrations. In fact, they'd evolved without it, so they began to die out. But as well, we can ask ourselves the question, where did the CO2 go? Well, there's essentially three ways. Number one, it was taken in by plants via photosynthesis to produce glucose and oxygen. Animals then ate those plants. When they died, they fell to the bottom of the oceans, where they were covered in sediment, so mud layers, and put in hot, high pressure, low oxygen conditions, where they formed sedimentary carbonate rocks, for example, limestone. The second way then was that ancient biomass was crushed by large-scale movements and heated to create fossil fuels. And we do need to learn two rock formations. So the first one is coal. Coal is a sedimentary rock, basically thick deposits of plant material like ferns died in swamps. There they were put in low oxygen conditions and compressed. We also need to learn the formation of crude oil and natural gas. So plankton forms to the bottom of the seabed, layers of rock build up on top. There they are trapped, put in hot, high pressure, low oxygen conditions. Those conditions over millions of years form crude oil and natural gas. If you are unsure on that one, jump back to our video on C9 to learn the formation of crude oil. And the final way that our CO2 concentrations decreased was that actually carbon dioxide dissolved into the water. There they reacted with metal oxides to form insoluble carbonate compounds, which precipitated, producing sediments, decreasing our CO2 concentration. But where did our methane and ammonia go? Well, our methane reacted with oxygen produced by photosynthesis to form carbon, and our ammonia reacted with oxygen to form nitrogen. Because nitrogen is a very unreactive gas, it was able to build up in our atmosphere. It's really important to note here, though, that all of this is theory. Scientists have found evidence from the oldest rocks on Earth that question the assumptions that early gases originated from volcanoes. Some believe that a mixture of gases were formed by solar debris similar to comets smashing into the Earth and vaporizing around 500 million years after it formed, and this idea has been peer-reviewed by other scientists. Our next mini topic then is climate change. So greenhouse gases in the atmosphere maintain the temperatures to support life on Earth, and there are 3 greenhouse gases that we need to know about: water vapour, methane and carbon dioxide. Greenhouse gases are just gases that absorb energy radiated from the Earth. Now, without the greenhouse effect, the Earth would be too cold to sustain life. However, humans are increasing levels too much, and that is leading to what we call the enhanced greenhouse effect that we don't want. We're warming up the Earth to levels higher than prehistoric times. So when short wavelength electromagnetic radiation, like UV rays, travel from the sun and hit the Earth's atmosphere, some rays reflect back into space, but most travel easily through the atmosphere and reach the Earth. And this is because short wavelength radiation does not interact with the gas molecules in the atmosphere strongly, so with our greenhouse gases. These waves are then absorbed by the Earth and essentially re-radiated by it as long wavelength terrestrial radiation, for example radio waves, and these hit the Earth's atmosphere, but because the atmosphere interacts with long wavelength radiation, the waves are trapped by it, and this heats the Earth up, and this is the greenhouse effect. So the long wavelength radiation, which is absorbed by the greenhouse gases in the atmosphere, causes the bonds in the greenhouse gases to vibrate more vigorously, and that is what causes the temperature to rise. Now, it's believed that human activities will cause the temperature of the atmosphere to increase, leading to global climate change. This idea has been peer-reviewed, and this is because we have a high concentration of greenhouse gases in the atmosphere, so that will increase energy absorption. CO2 has just recently increased from 0.03% to 0.04%. This seems like a small change, but it causes big differences. So how are humans increasing CO2 concentrations? Well, the first one is increased combustion of fossil fuels. The second one is deforestation. Now, deforestation increases CO2 levels but by 2 ways, essentially. The first one is loss of the carbon sink. When we cut down a tree, that tree stops photosynthesizing. It stops taking in carbon dioxide. But also, when you cut down a tree, it releases all the carbon stored in that tree over its lifetime just into the atmosphere. And the final way is that as humans are increasing the temperature of the Earth, the solubility of CO2 in water decreases, and this means that oceans reduce in their effectiveness as carbon sinks. How are humans increasing methane levels? Well, we've got an increasing population, and with an increasing population, we have increasing amounts of cattle farming. Now, cattle produce methane. We've also got increasing amounts of waste going to landfill, and it's decay of waste in landfill by microorganisms that produces methane. But we've also got increasing rice paddies and swamp fields, and this is because rice is the staple food of the world. With an increasing population, we have to feed those people, and rice paddies will actually release methane. And then we move on to the effects of global climate change. So the way to think of this is that we have 3 hydrological and 1 biological. We have flooding, extreme weather, changes in rainfall, and finally extinction. So we're going to look at flooding first. With increasing temperature, ice caps melt, and we also get thermal expansion of the seas. This causes sea levels to rise, and that can cause coastal erosion, habitat loss, and actually the loss of island settlements and communities as well. Our next one, extreme weather, well, we get increased frequency and strength, and so magnitude of storms, and that can cause damage. We also have changes in rainfall, so changes in the quantity of rainfall, when it rains, and where it rains. Too much heavy rain can damage crops, but with not enough rain, you can get drought, both of which can affect food supply. And then we have extinction. This is when, as our climate changes rapidly, animals and plants cannot adapt quick enough to the environment, and so they end up dying out. And then we touch on carbon footprint here. So this is a way of measuring the amount of CO2 and other greenhouse gases released over the full life cycle of a product, service, or event. Now, it's really hard to measure because we have so many different factors to consider. CO2 is released in extracting raw materials, manufacturing products, use and operation, and disposal at the end of useful life. And this means that obtaining precise measurements is next to impossible. Don't worry too much about this one. We will touch on it more in the next video. But we do have solutions to global climate change. So the first one that we look at is carbon capture and storage. This is when CO2 produced when burning fossil fuels in electricity production is stored deep underground in porous rocks. Porous rocks are just rocks with little holes in. And this usually takes place in redundant oil fields. However, this would make electricity about 10% more expensive. We could also look at plant-based diets. So methane produced by cows can be avoided if we eat less beef. Plant-based diets means that more land can be used to produce food for humans rather than food for animals like cows. That means that we have more efficient land use. We can also look at taxing fossil fuels and cars that burn lots of fossil fuels, and government support for biofuels. So biofuels are made from plant materials, and these plants have already done photosynthesis, so they've already absorbed their CO2. We could look at alternative methods of producing electricity, so renewables, wind and solar power, etc. Incentives for home insulation to decrease the combustion of fossil fuels and our use of fossil fuels for heating. But also carbon offset taxes, planting trees at the same rate as we burn them, so making companies carbon neutral. However, we have 3 problems with these solutions. Number 1 is that there is a scientific disagreement over the causes of climate change, and this leads to incomplete international cooperation. We also have the idea that it's really expensive for poorer countries, and poorer countries are often excluded from agreements and forced into solutions that may hinder their development. And the last one is that there is a lack of information and belief on a personal level that our contributions will help. So what actually is our evidence for climate change? Well, peer-checking scientific journals. However, a minority of scientists believe that climate change is caused by natural variations. Our hard evidence, if you like, is ice core analysis, analysing trapped air and oxygen isotopes. And then we move into the topic of atmospheric pollutants, and our first one is carbon monoxide. The best way to do this, I'd say, is to learn this little paragraph here. Carbon monoxide is absorbed by haemoglobin in your red blood cells instead of oxygen. This reduces the oxygen carrying capabilities of red blood cells. Cells cannot respire with CO, so a victim of carbon monoxide poisoning will become oxygen starved, they may become drowsy, they may lose consciousness, and they might even die. We then have sulfur dioxide, or SO2. This is an acidic gas that forms when the impurity sulfur in fossil fuels combusts in oxygen. S plus O2 makes SO2. This is your balance symbol equation for the formation of sulfur dioxide. There are two issues that sulfur dioxide causes. Number 1, it is a toxic gas, and number 2, it causes acid rain. Acid rain kills animal and plant life in lakes, but it also causes the weathering and erosion of metal structures that are particularly rich in calcium carbonate, for example, limestone. Sulfur dioxide emissions can be reduced by desulfurizing fuels before combustion occurs, or we can react sulfur dioxide, which is an acidic gas, with an alkali before it is emitted. So in coal power stations, we react to the flue gases, the waste gases, with calcium oxide or calcium hydroxide. We then have nitrogen oxides, NOx. At high temperatures in car engines, the usually unreactive nitrogen gas reacts with oxygen to form oxides of nitrogen. These are toxic gases, they can cause acid rain, and they cause respiratory problems, so they trigger or worsen asthma. Now, your balance symbol equation is 2NO2 makes N2 plus 2O2. You'll be fine as long as you can recognise that nitrogen comes as a diatomic molecule, N2, okay, so we've got N2 and O2 making 2NO2 if you balance that. And then we have particulates. Particulates are tiny solid particles containing carbon and unburnt hydrocarbons formed during incomplete combustion, mainly from diesel vehicles. Diesel is a larger hydrocarbon molecule, so it requires more oxygen to react with it. That means that it's more likely to combust incompletely. Particulates cause respiratory difficulties. They can damage cells in lungs and may even cause lung cancer. And they also cause global dimming. This is when particulates travel into the upper atmosphere and reflect sunlight back into space, causing a decrease in temperature. And that's all for this video. So well done if you made it to the end, and see you next time.